So welcome back to the classroom. We continue with our explorations of nth order linear non-homogeneous as well as homogeneous linear ODE of order n. And we use the notation, let Lx denote this expression that is given here, that is nth derivative of x plus p1 times n minus first derivative of x plus etc. pn tx, where we assume PITs are continuous functions on some interval t1 to t2. That's the assumption that we make. Now, the non-homogeneous equation then can be given in this form, in the normalized form, because I was telling you towards the end of the last lecture that why we are taking the leading coefficient to be equal to 1. Okay? If the leading coefficient has no zeros on this interval, then you can always divide by that and then write down the equation, and the two equations are equivalent in the sense that they have the same solution. But if the leading coefficient as vanishes at some point t on the interval t1 to t2, then you cannot divide by that, because you will see that once we set up the corresponding or equivalent system, you will see that the initial the existence and uniqueness theory that we have developed for the system is no more applicable, because that particular point becomes a singular point where the coefficient functions will fail to be continuous, and also all the other conditions required for invoking the existence and uniqueness theorem will not be valid. So we assume without loss of generality that the leading coefficient is equal to 1, and that is the so-called normalized form. It does not matter whether PI's vanish at some point or not, it is immaterial. Okay. Now the inhomogeneous equation is then of the form Lx plus Qt equal to 0, where Q is again defined on the same interval. Q is also assumed to be continuous on. These are the basic assumptions that we work with. Now you see that the first thing that we do is we convert this into a first order system. For that, we introduce new variables . So we start with putting x1 equal to x, and then write down the following equations. We have dx1 by dt, write as x2, dx2 by dt, and so on, dx n minus 1 by dt, write as xn. And then we have dxn by dt, that is given by this equation. This is equal to, push everything to the other side, you get minus p1 t xn minus p2t minus P&T x1. Now this is the case with the homogeneous equation. So we take the homogeneous equation. We are transforming this system into this form. Now let us define xt as and you write it as a column vector. If you want, you can put a transpose. Then we have the following. The equation is in the form dx by dt equal to x, where at is given by then we have the last row is given by minus P2 this is 8. And with this choice you have got the equation transforms into this particular form. Now we see that the equation, so I'll use this as 1, 2, this is 3. The equation Lx equal to 0 is equivalent to the system 4. Now you see that from the assumptions, we have assumed that all the PIs are continuous. It follows that the existence and uniqueness theorem is applicable for equation 4, and there exists a unique solution on the interval. That means on the interval t1 to t2 there exists a unique solution of the initial value problem, dx by dt equal to atx. So the initial value problem is this. where x naught is some vector in R. Okay. Now let us first of all look at what is the condition, initial condition for the equivalent nth order equation. What does this translate to? See, equation 3. You see that the first component, see what is x t naught? X t naught is the first component is x1. Okay. So x1, so it amounts the following. Suppose x naught n naught belonging to R. Now you see that your x1 at t naught is then equal to x1 naught. So this is, so you have x1 derivative at t naught equal to x2 naught and so on, x1 n minus 1 derivative at t naught equal to x. Okay, because this comes from the our transformation that we have used. We have started with x1 and x1 derivative has been written as x2. So x2 at t naught is essentially x2 naught. So that is x1 derivative. Then you can make everything in the language of x1. So you see that x1t is a solution. Therefore, if xt then x1t, x equal to x1t is a solution of, that is the first component of the vector, is a solution of the homogeneous equation with initial conditions x1 t naught x n minus first derivative at t naught equal to so the equivalent the translation of the initial data is prescribing the function as well as all its derivatives up to the order n minus 1 at some point t naught. Okay, for the system it was prescribing every component of the vector x. Now, so this is a very special case of the nth order system that we are using. And you see that what is the solution of this nth order equation? The solution of the nth order equation is the first component of the solution of the equivalent system. Of the first order system equivalent to equal to 0 is given by the first component of the solution of the system. So we have on one side you have the equation Lx equal to 0 with x t naught equal to x1 naught xn naught. The equivalent system that you have is this dx by dt at x with the condition that x t naught equal to x naught. Okay, so if you can show that there exists a unique solution under the conditions for which there exists a unique solution of this initial value problem, the first component of that solution will give you the solution of this initial value problem. Okay, so the two are related. Conversely, if you know the solution of this initial value problem, then the vector xt written as whatever be the, okay, let me denote that solution by phi t, phi 1 t. If you take this vector xt as this, then this becomes the solution of the corresponding initial value problem. So you can go back and forth from the nth order system, the nth order equation to the nth order initial value problem to the corresponding initial value problem for the equivalent system. Okay, so all the theorems that we have so far proved on this homogeneous equation is valid here also. Let me also make a remark in the passing. What is the inhomogeneous equation? What about the inhomogeneous equation? So corresponding to the inhomogeneous equation, the inhomogeneous you can translate into a system. So what it amounts to, we will have to obtain CTs of the form dx by dt equal to at x plus bt. What is this bt? So the corresponding equation that you have is Lx equal to 0. Okay. Therefore, you see that this bt will become essentially the first component will be dt and all other components are going to be 0. Okay. So you take bt as the column vector bt 0. So that will give you the corresponding equivalent system. Or sorry, sorry, it will be other way around. Minus bt. This is the system. And you see that the conditions for the system, once bt is also is there, if you assume bt is continuous, then you see that there exists a unique solution for the inhomogeneous initial value problem. But we will revisit this particular case later. Okay. So right now we focus on the homogeneous system, homogeneous equation. Immediately see that the relation between the two solutions are, if you know phi is a solution of Lx equal to 0 satisfying these conditions, then xt defined as phi t, phi derivative of t, etc., phi n minus 1 derivative of t will be the solution of the equivalent system subject to these conditions. Conversely, if you know the solution of this particular system, then the first component of xt will be the solution of the nth order equation. So that is the equivalent, equivalence of the two. Now we observe the following. The first thing that you observe is that if you take Lx equal to 0, then you see that the set of all, so if I call this collection as, I'll give some name, which requires x to be n times continuously differentiable. Okay. So x belongs to Cn, t1 to t2, so that all the n derivatives are exist and are continuous, and you can write Lx equal to, Lx can be computed, and the set of all such x's, that is Cn functions defined on the interval t1 t2 such that Lx equal to 0 is a vector space. See that xt identically equal to 0 is a solution of the system. Therefore, 0 belongs to that, and you can show that if x1 and x2 are two solutions of the system, then x1 plus x2 is also a solution of the system, of the nth order equation. So if x1 and x2 are two solutions of the nth order equation, then their sum or n more generally a linear combination of them of the form C1x1 plus C2x2 or any C1 and C2 is also a solution of the equation. Therefore, S is a linear space. Now, what is the corresponding vector space that you have? You have got the corresponding equation dx by dt you have seen that this homogeneous system has a vector space which is, we know a lot about it. In fact, we know much more about it. What we know is that this is a vector space of dimension n. Okay, that means you have a fundamental system of solutions of the system which turns out to be a basis for the solutions of this. Now, the correspondence of a solution of Lx equal to 0 and to that of the linear system and vice versa just tells you that suppose of which is a basis solution space, then the first components of form a linearly independent system, linearly independent set of solutions Lx equal to 0 and is a basis this is the connection. Okay, how do you prove that? It's quite easy to prove because you start with, see, what you want to show is this: take with Lx equal to 0, transform this into the system. So you have got dx by dt x. Now suppose we have already got a basis x. Then what you have? You have the first component of all this. Let me call that phi 1, phi n. First components of Excellent. Now what do you know? Suppose we start with an arbitrary, so see, and they are solutions of Lx equal to 0. Okay. So you know that if these vectors are linearly independent, then the functions phi 1, phi 2, etc., phi n are also linearly independent. Why is it so? So C1 x1 plus C2 x2 plus etc. Cn xn equal to 0 implies C1 equal to 0, C2 equal to 0, etc. Cn equal to 0. Right? Now, let us see what we want to. There are a few assertions that we make. And they are solutions of this, that is clear. So the question is whether they are linearly independent or not. Now what are the corresponding x1, x2, etc., xn? So if you take these functions, the corresponding solutions x1, x2, xn are xit equal to phi I the n minus first derivative of t. You can form a column vector. Okay. So they are the corresponding solutions of the system. Okay. So the relation between these x1, x2, etc., xn and phi 1, phi 2, phi n, which are the first components of x1, x2, etc., xn, is this. Okay. Xit consists of this particular column vector. So you have got x1t, x2t, etc., xnt corresponding to this. So if we start with a linearly, what we want to prove is that this is linearly independent. Now look at this one. If they are linearly independent, then this is also linearly independent. Why? Because you take C1 x1 plus C2 x2 plus etc. Cn xn equal to 0 implies C1 equal to 0, C2 equal to 0, etc. Cn equal to 0. Okay. Or from this relation that you know that x1, x2, etc., xn are linearly independent, therefore the coefficients, the linear combination of this is equal to 0 if and only if C1, C2, etc., Cn equal to 0, which says that the coefficients of, that is C1 phi 1 plus C2 phi 2, etc., Cn phi n equal to, identically equal to 0 implies C1 equal to 0, C2 equal to 0, etc., Cn equal to 0. Therefore, these functions are linearly independent solutions. And you cannot have more than n linearly, in a set of linearly independent set of solutions, you cannot have more than n functions. Okay. That is because in that case, the corresponding set of vectors, the xit that you make will also form a linearly independent set, which is impossible. Okay. That we have already proved. Therefore, you see that the space of solutions of the homogeneous equation has phi 1, phi 2, etc., phi n linearly independent. So this is the connection between the two. Okay. So we will write it out in the form of a theorem. So on one side you have this system and on the other side you have the nth order equation. The two are connected, and you see that a basis for the equivalent nth order system, the first order system of n equations, give you n solutions of the homogeneous equations which are also linearly independent. And this also spans the whole space. Why it is so? Suppose equation equal to 0. Now we claim independent solutions of equal to 0. Then what do you have? You have the corresponding solution corresponding to x equal to phi t is now corresponding to this phi 1, phi 2, phi n, you have the equivalent so these are the this one correspond to now you write down this. What we have is that if phi i's are linearly independent, phi 1, phi 2, etc., phi n is linearly independent, then x1, x2, etc., xn is linearly independent, and vice versa. Okay? Therefore, xt can be written as xn, because you know that this forms a basis for the solution space of the system. Okay, therefore any solution of the system can be written in this particular form. In particular, the xt that we have worked out from phi can be written as in this particular form. Okay, what does this mean? This means phi t, which is the first component of that, this is equal to c1 cn phi n t, or in other words, the given solution or the given solution phi t can be written as the as a linear combination of phi 1, phi 2, etc., phi n. Therefore, this we started with an arbitrary solution of this equation. So every solution can be written as a linear combination of phi 1, phi 2, etc. Phi. What does it mean? That this collection phi 1, phi 2, phi n spans, yes, it's also linearly independent, therefore so I leave it to you to write down a proof of this, show that if and only if for the solution space of what I mean to say, the solution space of Lx equal to 0. This is one. Once we establish, of course, that is to be, you give a detailed proof for this particular result. In fact, we have the following theorem, namely, I will give the statement of the theorem. The homogeneous equation, so let me write down the statement of the theorem. So we make an observation. Suppose, okay, before that we write down the following theorem. We get the statement. The homogeneous equation Lx equal to 0 has a fundamental set of solutions consisting of in solutions of the equation. That is what we have described here, phi 1, phi 2, etc. Phi. So we have a set of functions phi n. Write these here, n solutions of format mental set of solutions if they are form a linearly independent set of functions. And this is equivalent to the so-called Wronskian this is the determinant, not the matrix alone. This is the Wronskian determinant. Okay. Vanish for any t, which is equivalent to saying that it does not vanish for the statement that at some t naught okay, what is the Wronskian determinant? How is it related to the other solution? So let us just investigate this connection. Suppose Now you see that corresponding to phi I, the solution see xi is a if and only if phi I, that is the first component of this, is a solution of equal to 0. Now, of course, here we are taking dx by dt equal to at x, where at is the corresponding the matrix constructed out of the coefficients of L as described earlier. And right here. That we have described earlier. Therefore, xi form a linearly independent set. If xi form a basis, then these vectors are linearly form a set of n linearly independent vectors, and naturally phi i's are linearly independent. So ATX. Therefore, whenever x1, x2, etc., xn forms a basis for the solution space of this, phi 1, phi 2, etc., phi n forms a basis for the solution space of nx equal to 0. Okay. Now, what we observe is this: since if x1 then what we have is the determinant of is not equal to 0. Okay. Why do we say that? That means this set of, the meaning of this is that, see, if you write down this as, suppose I write this as, say, look at this as a matrix. Suppose you look at this matrix. See, the determinant of this is equal to 0 if and only if the rank of this matrix or this matrix is less than n. Okay, the determinant of this is not equal to 0 means the rank of this matrix is equal to n. Okay, so that is a connection between the two, right? And what is this when you connect with phi? This is the same as, suppose you take the first component to be phi 1, phi 2, etc., phi n, then this is phi 1 derivative this is n minus 1 derivative. This is phi n minus 1 derivative. So this matrix is essentially equal to this matrix. But what is this? This is okay. This is W phi 1, phi 2, etc., phi n. So if they are, this forms a linearly independent set of solutions. Correspondingly, this matrix has rank n. This means this matrix has rank n, or the determinant of this is not equal to 0. So it's not this one. So this is equal to, I'll write this. So wrongly. So it is the determinant of that. So determinant of is not equal to 0 if and only the Wronskian of not equal to 0. That is the connection between the two, essentially, because they are related to the same equation. And you know that these vectors are linearly independent if this is not equal to 0, which is equivalent to saying that the Wronskian is not equal to 0. Okay. So in the second order case, I mean, let me just write down. I mean, this you may be familiar with it in the second order case. So let us consider the example. Suppose this is the equation. Okay. Then this I can write in the form. So I introduce the notation x1 equal to, then what I have is this dx1 by dt dx2 by, what is dx2 by dt? dx2 by dt is equal to d2 x1 by dt square Yeah. Okay. Yeah, I'll stop with this statement. Thank you. Yeah. Now this I can write as minus P1 so will you work this out? Okay. So I will work this out for will you please work out this the details of this? Okay, I'll stop now. Yeah. So okay. Right. Thank you very much. Okay. Yeah. Will you work it out for this particular example? This is an example on which you can work out the details, and then after that you go to the generalization. Okay, thank you very much. I will stop here. Okay, I just write it. Just